of the beginning of the universe, Magic by Higgs Boson. I'm very pleased to see so many of you here on this cold Cyprus evening. Thank you for coming. And we have a real pleasure to have with us today Professor Shoji Asai, Director General, High Energy Accelerator Research Organization, KEK, Japan. And I would like to call to the podium Professor Stavros Malas, President of the Cyprus Institute, for his welcome address.
Okay, good evening, everybody. Again, let me start by welcoming, in addition to the ambassador, representatives from the Serbian Republic, from Greece, and of course the Foreign Ministry of the Republic of Cyprus. Now, for those that have not been with us this morning, we have an event here, Cyprus meets Japan, Japan meets Cyprus, which has been very productive. I can see you all very enthusiastic about this very easy lecture about the origin of universe. So I can promise you the dinner tonight will be nice. It will be fish. It will be cooked, however. So now, when I was looking at this title, it reminded me when I was a student at undergraduate student studying genetics. So I'm sure you're aware there are two major challenges in understanding the origin of universe is, of course, the origin of universe, which is what we're going to hear. I think it happened, 13, 14 billion years ago, something like that. And then about 8 billion years later, we have the origin of life. And that's when my discipline starts functioning. And these Big Bang theories and so on, it's being quite a challenge. Now, this morning we heard, there was a talk by one of the colleagues here about how a single channel opens in the membrane of a cell. Now, you can understand that takes a lot of time to study. The complexity of a single cell, let alone studying the assembly of a single cell from organic molecules. And that's really going to take probably several hundreds and thousands of years, well, I say hundreds, for modern science to be able to understand. So I'm sure it will be quite simple because it's for lay people, I understand, this lecture, and we look forward to it. Thank you very much for being with us.
I call to the podium His Excellency, Ambassador Extraordinary and Plenipotentiary of Japan to Cyprus, Yoshio Yanawaki, for his welcome address.
So good evening, Kalispera sas. Thank you very much for joining us tonight. It's my great pleasure to be here for the opening of the public lecture by Cyprus Institute and KEK. KEK is a High Energy Accelerator Research Organization from Japan. And thank you, Cyprus Institute, for giving us this opportunity to deepen our collaboration between Japan and Cyprus. KEK is a prominent institute in Japan that has been at the forefront of the development of particle accelerators and related technologies. It conducts experimental and theoretical research on elementary particle and nuclear atomic nuclei, and on the structure and the function of various materials, including life. And Nobel laureates in physics have conducted research at KEK. Today, Professor Asai, Director General of KEK, will give a lecture on the beginning of the universe, which has always fascinated many people, including me, and the progress of the research after the discovery of the Higgs Boson in 2012. and he and his colleague from Japan are visiting Cyprus to hold a 3-day interactive symposium and workshop, which is very important for us to get to know each other and to explore the possibility of future cooperation. So I'd like to thank Professor Asai again and express my sincere gratitude for this opportunity. And I hope you all enjoy tonight's event. And after this lecture, we were having some reception, and I brought some bottles of Japanese sake, so I hope you will enjoy also our product. Thank you very much.
Your Excellencies, dear colleagues, dear friends, now it is time to introduce our speaker this evening in this public lecture co-organized by 3 parties, the Cyprus Institute, KEK, and the Embassy of Japan in Cyprus. I would like to call to the podium Dr. Taku Yamanaka, Senior Research Administrator, High Energy Accelerator Research Organization, KEK, and Professor Emeritus, Osaka University, who will deliver a short introduction to our speaker tonight.
Thank you. So let me give a brief introduction of Asai-san. Well, actually in Japan, among physicists, we just put san at the end of the last name to show the friendliness, and that's how we usually call him. So Asai-san is actually a brand new Director General of KK because he's just started in April this year. And before then, he had been a professor at Tokyo University of Tokyo. And actually, he spent many years at CERN, which is a big international laboratory at Geneva, in Switzerland. He had actually worked on E plus E minus electron and positron collider, and also on LHC, which is the proton-proton collider. And he has been searching for a thing called supersymmetric particles, and also had been searching for Higgs, and which his team or the group actually discovered the Higgs particle. But in addition, he has many hobbies, and I'm sure he will see a glimpse of his hobbies, and but it's just one of them, I think. And he's also fond of cats. And in the KK, I often see him walking with some small, what is it, food for a cat. And so I'm sure, and I think he has been looking for cats in the Cyprus also. But anyway, we're expecting interesting question. Okay, and that's the insanity of the beginning of the universe. So let's welcome Asai-san. Right.
Your Excellencies, ladies and gentlemen, dear colleagues, dear friends, it is now our great pleasure to welcome to the podium our public lecture speaker tonight, the distinguished Professor Shoji Asai, Director General of KEK. Professor Asai, the floor is yours.
So thank you very much for the opportunity for the presentation today. So good evening, everybody. So I talk about 40 billion years ago, our universe created. At that time, unbelievable, very insanity things happened. The particle physicist, I'm particle physicist, that has no common sense. So I think maybe the particle physics is very suitable for these topics. So at first, we start with let's start with the universe. I like astrophotos, so every night I'm very busy. I take of these photos. So what is galaxy? Closest galaxy is Andromeda. Even in the closest, but about 2.5 million light years away from here. So this light, you see, is about 2.5 million years ago. So at that time, there are no human beings in our Earth. Yeah. So our galaxy has also the similar shape and similar size. So typically, 1 trillion stars existed in the one galaxy. So 10 to 12 stars, like the sun, is existing in the one galaxy. This is the galaxy. Then the very dark region in our space is observed by the Hubble telescope. Then this picture is obtained. This is not a star. This is a star, but this is not a star. This is a galaxy. So galaxy. There are many, many galaxies observed in the dark areas. So in our observable regions, in our universe, so the galaxies existing about of the 300, it's very difficult to count, 300 billion galaxies exist. So 10 to 11, more familiar for us, this. In this case, so the typical, I have said, typically the 10 to 12 stars in the one galaxy. So it's times, then the star, like a sun existing in our universe, is about 3 times 10 to 23. I cannot how to say that in English, this one here. But 10 to 23, the star is existing. 10 to 23 is Avogadro's numbers. So Avogadro's number star is existing in our universe, observable region. So there are many materials, 10 to 54 kilograms existing in our universe. So there are many materials existing in our universe. Who made such many materials? For example, 100 years ago, so that we believe universe was considered as stable. Even Albert Einstein also considered universe is stable. So in this case, nobody is prepared for the material, just existing materials. And so eternally exist before our time start. This 100 years ago, so we considered as this was. But now, the revolution. So about 100 years ago, Hubble discovered expansion of the universe. Hubble telescope is the name of he's Dr. Hubble's. 100 years ago, not 100, maybe 70, 80 years ago, so we can smoke near the equipment. Now we, yeah. But at that time, it's a very comfortable age, so we can smoke. So he measured color of the galaxies. So this is using a prism, he measured colors. So then the redshift. Redshift shows the velocity of the recession. So if the object is far away, in this case, light becomes more red. So, and this red is proportional to the velocity of the recession. So he measured of this shift as a function of the distance of the galaxy. So this is the distance of the galaxy, and this is the velocity of the recession. He plotted, and then he make one line. This is very revolutionary. At that time, person believes the cosmology, space is stable, but he make this line. Of course, this line is currently wrong. But his estimation is much, much higher than true values, but he made this line. So important things is galaxy fly away. So our universe is expand. This is a very important discovery about 100 years ago. So the expansion means that, so go back to the past. So now the expanding, then go back to the past. Then the universe becomes smaller, smaller, and finally it becomes a point. So this point is called Big Bang. So this is a picture of our universe now. The size, currently the size of our universe is about 50 billion light years. So diameter is about 10 to 24 kilometers, very huge spaces. Currently our universe is very large and still expanding. So the recently, but 3.8 billion years ago, expansion accelerated by the dark energy. This is a discovery by about 20 years ago. So then go back to the Big Bang. Before the Big Bang, the cosmological scientist says, before the Big Bang, there was nothing. Even space and time is nothing at that time, he said. They said, I'm sorry, they said. Why the nothing made our universe? And what is a Big Bang? And why does not energy conservation, since currently we have a huge energies and huge materials, but here's nothing. Why the nothing make such a materials and such a big energies? So it's very difficult question. So this question, this question is a vacuum. Vacuum is very important topics. So the astronomers cannot probe the Big Bang directly, since we can see the light after about 380,000 years later after the Big Bang. So you can see the Kobe data. This is for the fluctuation of the light. This is the latest light. This is the oldest light. Before the 380,000 years ago, there are no light coming here. So the particle physicists study the point of the Big Bang directly. So the particle physicists using a vacuum, nothing's vacuum, using a big colliders. So let's move to the particle physics. So at first, I summarize of the hierarchy of the materials. So let's image of the water. So water is H2O, the molecules. And the molecule is formed by the atoms. So for example, H2O is one oxygen atom plus 2 hydrogens. This is the atoms. So size of the atom is 10 to minus 10 meters. It means about 1/10 billion meters. So from the Greek age to the early of the modern age, this atom is considered as elementary particles. But about 110 years ago, Rutherford discovered a nuclear, and Thomson discovered of this electron. So the center of the atoms, the atomic nucleus is existing, and also the electron existing. And the atomic molecules is formed by the proton and the neutrons. About before 60 years ago, these considered as elementary particles. The size of the nucleus is about 10 to minus 15 meters. So it means 1/10 petameters. It's very difficult. Yes. So for example, you often see these figures in your textbooks. So the large nucleus existed at the center of the atoms and the electrons around it. But this picture was wrong. So for example, if this atom is compared with football stadiums, in this case, so the nucleus is just 1 cent coin on the center circles. This is very small. And the electron not round. just electron existing around of the audience seat. And sometimes appears here, sometimes appears here, sometimes appears here. We cannot predict where is it. But it's randomly existing, and just the probability is calculated by these formulas. This is the material. So this space, this is empty. So the material is very empty. Imagine of the gold. I'm sorry, I don't have the gold. So imagine the gold. Gold is very heavy, dense, and very expensive. But even in gold, in atomic levels, it's very empty. So the material is very empty. Why the electron is crushed to the squeezed? It's very difficult question. Currently, we don't have answer for these questions. Just for the quantum mechanics, give some answers, but we don't know the why currently. So this is 60 years ago. So 60 years ago, we discovered another structures. So the currently is, so the proton and the neutron is formed by the quarks. For example, the two up-type quark plus one down-type quark makes a proton, and the two types of the down-type quarks plus one for one up-type quark make neutrons. This is just 60 years ago discovered. I often asked, what size of the elementary particles? The answer is no size. Let's imagine if exists size. In this case, it means size is existing like this. In this case, there are some things inside of this material. In this case, this becomes not elementaries. Elementaries existing in this one. So by definition, the elementary particle has no size. Currently, we understanding the upper limit of the elementary particle size is less than 10 to minus 90 meters. This energy is determined by the collider energy. In futures, we make a more high energy collider. In this case, we can examine the more small regions. So in this case, maybe we can find structure in electron and quarks. So in this case, it becomes, they are not elementary particles. We will have another elementary particles. So this is the structure of the hierarchy of the materials. So there are two types, there are two types of the elementary particle has observed in the previous research. The type 1 makes materials. So every material makes this type of the quarks and leptons. So for example, so the structure of the atoms, so the nucleus are formed by the quarks, up-type quark and down-type quark, and the electron is elementary particle, plus neutrino, and make a one family. So up-type, down-type, electron and neutrino makes a one generation. We have 3 generations. Why 3? We don't have answers, but there are 3 generations existing. And almost all our world is almost made by the first generation. There are no necessary of the second and third generation for our world, but there are 3 generations is existing. The muon is a big brother of the electron. This muon is very important for the heritage science. So, for example, the passive waves. So the muon is fall from the sky. So every second, please image your hand. Every second, one muon is a pass in this region. So there are many muon. It comes from the sky. So let's image of the pyramid. So the muon penetrates through the rock and the materials, but slightly absorbed in these materials. So that we can estimate how many materials existing before the detectors. So this is the method we discovered of the unknown void space in the pyramid. This is the pyramid, scan pyramid project. The KK also joined this project. And not only the pyramid, but also the Japanese ancient tombs is used for this technology. And also the Roman ruins can be discovered of the using the MIMO method. This is the passive way. For the active way, the KK produced muon and neutron artificially using J-parts. So the LINAC and cyclotron, and then we can produce many protons and hit the target, then produce the muon and neutrons, and we can use the muon and neutron for life science and also material science and also the heritage science here. For example, we probed 200 years old medicines. If we can open, then the oxygen is inside. So material, everything is changed. So we cannot open. But we can measure for what materials existing in these bottles using X-ray, muon, and neutrons. So we can estimate these ones. So the muon is very important for the heritage science, and muon is the big brother of the electrons. So this is a type 1. So everybody in our universe is made by the type 1 elementary particles. And type 2 elementary particle is propagate force. What means propagate force? So, for example, I became shorter. So for particle A, this is the material particles, and also the particle B is the material particles, and exchange of the particles. So this is called the gauge boson. So then exchange of the particles, then the particle A and particle B feel the force. So this is the particle propagate force. This is the type 2 particles. There are 4 forces in our universe. So the gravity and the electromagnetic are very famous, very familiar for us. But yes, there's another 2 types of the forces existing. So gravity is propagated by the graviton. But this graviton has not yet discovered. Maybe the end of this century, I hope the discovery of the graviton. So discovery of the graviton is very difficult. Maybe the quantum technology is very useful to discover of the graviton. But the gravity is very weak. Comparing 10 to minus 42 is weaker than the electromagnetic force. So currently, the particle physics ignored of the gravity. So the graviton is not so necessary for our understanding of the particle physics. So the second familiar force is electromagnetic force. Electromagnetic force propagated by the photon. Photon is very famous. You can see this light. So this is the feeling of the force. So then our sensor is changed. So we feel the light. So this is the reason why the photon is propagated to the electromagnetic force. Another force is a strong force. Nuclear size is 10 to minus 15 meters, very small regions. The quark is concentrated in a small region due to the strong force. This strong force is propagated by the gluons. And also the weak force is existing. So for the neutron is a change into the proton plus electron plus neutrino. So the radioisotope is changed. This is due to the weak force. This weak force is propagated to the W plus Z. About 40 years ago, so the CERN discovered of these particles. So this is a second type of the elementary particles propagated by force. In about 10 years ago, we know that these two type particles, material and force, but still missing. What is missing? This is the origin of the mass. So all particles should be massless and move with the light velocities. But many particles have mass and move is slower than the light. So the particle physicists don't like diversity. So currently we respect to the diversity, but particle physicists don't like diversity. Yeah. So the particle physics should be unified. Is very important. So, but our world. So this is the ideal world. On the other hand, the real world has a particle have some mass and move slower than the light. Why? So our world occupied with something. So something affect the movement. For example, the W is very heavy, so resistance is the movement. Then they have some mass. So we consider like this one. So our field is considered the field with some things. This basic idea is spontaneous symmetry breaking, proposed by the number sensei about 70 years ago, maybe around 60 years ago. Yeah. It means that when our universe cooled down, then the symmetry breaking, then our space was occupied something. This is the basic idea of the spontaneous symmetry breaking. What is something? This is very important. So what is something? For example, the magnetic field. Let's imagine a magnetic field. So you can see it, magnetic field. Since, for example, this is a strong region, and this is a very weak region. So weak and strong exist. In this case, it is easy to understand. So on the other hand, something is a vacuum field. So the vacuum field is uniform and constant. Constant means does not change as a function of the times. So in our universe, so we cannot recognize the feeling of something. So it's very difficult to detect of such something. How to probe this one? So for example, let's image of the magnetic force. For example, given the energy to the field, it means the drive to this magnetic field. Then you can obtain some voltage. I don't know how to say it, length law or something there. In this case, so another saying, if they give you the energy to the field, then we can obtain the photon. Same things considered. When we give some energy to this vacuum field, then the excitation, then we will observe this new particles. So this is a method of how to probe this something. Then how to give the energy to the vacuum? This is a very difficult question. So the high energy particles collide with the high energy antiparticle, then they disappear. Just energy remains. What is the antiparticles? Antiparticle is the same as the particles, but the charge has opposite. For example, the electron has the antiparticle of the positrons. The mass is exactly same, and everything is same except for the charge. So this is the antiparticle. So particle and antiparticle prime disappear, since plus and minus. So everything disappears. But just energy remains. So this energy is deposited to this vacuum field something. If the vacuum field does not exist, then the energy is go back to again the particle antiparticles. So, but if some vacuum field exists, then the excitation is expected. Then the Higgs field is excited, then Higgs particle is produced. So if the energy deposited to the vacuum, then the Higgs particle produced from the nothings. In this means in a vacuum. So something is hidden in our vacuums. So this is the principles of our experiment. So how to make a collide of the high energy particles and antiparticles. So the cell makes large collider, Large Hadron Collider, LHC. This is a picture of the Geneva. This is the Geneva airport. And the old city of the Geneva is here. And this is the Lac Le Mans. And you can see the Swiss Alps. And under the 100 meters, so the circumference 27 kilometers. So it means the diameter is about 9 kilometers. And you can see there's some tunnels. And in these tunnels, LHC accelerator is installed. And in this accelerator, the protons are accelerated up to the 99.9999998. 89 is existing, yeah, I'm sorry, yeah, of the light speed. So they have high energies. So 27 kilometers is very difficult to image. For Japanese, the 70 kilometers is almost of the Yamanote line in the center of the Tokyo. But in Cyprus peoples, for the 27 kilometers is completely covered by the city of the Nicosia. The very big accelerators. Now CERN considered more larger ones, almost 100 kilometers. Factor 4 larger. So in this case, we cannot see in this same pages. So I'm afraid for this point. Bigger is not so good for the sustainability. Sustainability means circumstance and also the cost. Both sides is very difficult, I think so. And the LHC was constructed by the CERN. And the US and Japan contributed about 10%, but 90% covered by the European countries. The CERN is the largest international laboratory for the particle physics. There are 4 big international laboratories. So the United States have a Fermi National Labs near the Chicago, and in Japan the KK, and in China is the IHEP. These 4 is the big ones. But CERN is the largest one in 4 national labs. And CERN has 24 member states in Europe and located at Geneva. And this is the Geneva side, and between, just on the border of the Switzerland and France, CERN is located. And Cyprus is the associate member of the CERN about 8 years ago. And Japan and the US are observer state. So let's image, in order to give the more image of the accelerator, so I prepared for the videos here. So this is a picture above the cells. There are many buildings existing in the cells, and there are many grapes for the wines. Coteau de Rhône is a very famous wine for near the Geneva. Yeah. And under the ground, I'm sorry, this is a Japanese. And there are some tunnels existing. And there are 8 shafts to the access to this tunnel. And this is a picture of the tunnels and located at the accelerators. And technician people is visiting using electric bikes and to the repairs of everything. So this is a superconducting. So the temperature is about 2 kelvins, very low temperature. So the very difficult accelerators. So that this is the images, and this is also images. This is the real ones. Yeah. And in these big pipes, we have vacuum pipes. In the vacuum pipes, many proton is accelerated and accelerated, and the opposite side is also accelerated, and sometimes it collide in the center of the detectors. Then something happened. Yeah. So, okay. Okay, so just collide. The Higgs is appeared or disappeared, but they decay into immediate. So that we cannot see directly observe the Higgs boson itself. So in order to detect the Higgs bosons, Atlas detector and CMS detectors are prepared. For the both detectors, what happened at the collision point is exactly obtained. For example, it's decay. So some particle is emitted. So what type of the particle is emitted, which direction, and whose energy is precisely measurement. Then we can understand what happened in the centers. This is the detectors. So this is the Atlas detector. Japan joined Atlas detectors. So diameter is 22 meters, and length is about 44 meters, two big ones. And also the high precision sensor is in this one, about 200 million channels existing in these detectors. And this is a human size. It's very difficult to see the red wares on the red ball, but this is the very big ones. And University of the Cyprus joined the CMS detectors. So let's see the, okay. So the Higgs boson is produced and decay into immediateries. And I have said which particles, whose energy and whose direction is precisely measured. Then we can measure what happened in the center. This is a picture of the Atlas detector. This big one, Japan made these big detectors. So for the detection of the mu ones, yeah, the very big ones. Not only the bigs, but also there are many cable, gas, and high energy voltage is necessary. So that there are very complicated cables. So it's very tired for making this one here. Everything is inside, underground of the 100 meter rate depth. So every part is just prepared on the surface, then they go down to the down, and making make something, make setups in the inside of the this one. Yeah, sorry. This is the NHK videos here. So let's move to, okay. So we have collided proton and proton more than 2,000, about 3,000 trillion times. So there are many times that collided. This is a candidate event of the Higgs decay into 4 muons. This green one is electron, and this red one the muons. So we measured the electron and the muon precisely. Then we can estimate what happened in these centers. So next page is the real data. Please look carefully. So this one. Why so we have to collide many times? So this is the reason why God likes dice. So this is the invariant mass distribution of the outgoing particles. So if the outgoing particles comes from the one particles, in this case, this value is concentrated over some particles. There are many backgrounds. The two particles is observed. In this case, these two particles comes from the independent. In this case, this invariant mass distribution becomes a random. This is the background. If these two particles comes from the one particle, then the invariant mass shows the mass of these particles. So this is the reason why you can see the very beautiful peaks. So, but their background is existing. So our world is determined by just probabilities. So sometimes the fake phenomena looks like a great discovery due to the statistical fluctuation. So this fluctuation probability is required to be less than 1/millions. This is the condition of the discovery. This is the reason why we have to collide many times. You don't believe, you look like a real ones. But for the particle physicist, this is a very beautiful peaks. Wow! At that time, we have already conceived maybe something's existing there. So, about 10 years ago, July, the discovery of the Higgs boson. Discovery was reported very widely in the newspapers. There are many newspapers in the top pages, and TV and radio, and also the internet. And Higgs boson became very famous. I cannot understand that. But and also the Peter Higgs and Angren win the Nobel Prize very quickly. Why so exciting? So the next is the significance of the discovery of the Higgs boson. Higgs particle itself is not so important. Important things is Higgs field. Higgs field existing is very important. Higgs particle is produced from the vacuums. So our universe, it means our universe is filled with the Higgs field. And this is the origin of the mass. So I have already said that type 1 particle makes materials, quark and lepton. And type 2 particle is propagate the force. There were the two types of the particle has already discovered. And Higgs boson is not so important. Higgs field is very important. That our vacuum is filled with the Higgs field. So this field exists in all of our universe. So the vacuum was considered as empty before the discovery of the Higgs boson. But we discovered that vacuum is not empty, but filled with a mysterious field. But this mysterious field plays important roles of the beginning of our universe. Next page. So let's imagine the usual energies. Usual energy for me, examples for energy of the material or something. So energy of the gas and energy of the liquid or the energy of the solid or something. So if the volume is expanded by factor 2, then the energy density becomes high. You accept naturally this image. But this image is just particle pictures. Let's imagine, for example, so for 3 particles considered in this space, volume is expanded by the factor 2, but particle number is just 3 are the same. So this is the reason why the density of the particle density becomes half. But the vacuum field is different. Nothing a particle picture. So if the size of the volume is expanded by the factor 2, but density does not change. So that important, this is a vacuum field picture, is quite different from the particle pictures. What happened in this case? So we have a miracle due to the strangeness of the vacuum field. When let's imagine some energy in the vacuums. Vacuum field have some energies, and then the vacuum volume is expanded by the factor 2. Then density does not change, and the size of the volume is a factor 2 change. Then the energy is a factor 2 increase. So the energy gained. So this is a free lunch. But the factor 2 is not so enough, you feel. Important things is inflation exists in our universe, in our state. So the inflation of the universe, the volume of our universe, the larger and larger, by factor 10 to 30 to 10 to 40, it's too very big. Then the energy of the universe are also the bigger than factor 10 to 30 and 40. So the vacuum produced the energy of our universe. This is the origin of the Big Bang. Now we consider as follows. This is a still hypothesis, not yet determined by the experiment. So the quantum fluctuation make a small universe. Let's imagine your front. So you can see it. You cannot see, but so there are many universes. Small size universe is just in front of you. So but every time, every 4 years. But this universe, the size is very small. Maybe the 10 to 35 meters, very small universe. Usually, less fluctuation is stable. In this case, this small universe is disappeared very quickly, maybe within the 10 to minus 44 seconds, disappear. But we don't know the why. But if the energy of the fluctuated case is stated becomes lower, it is spontaneous symmetry breaking by number sensor. In this case, space is inflated naturally. So the small universe has a small energy, but becomes, since there are some small energies, then the universe becomes inflation. So inflation occurs naturally in this case. In such unstable situation, the size of the universe becomes very large, 10 to 30 or 10 to 40 size of the universe. Universe at first 10 to minus 35, then the inflation the times this factor, finally the first universe is about size is about 100 meters. This inflation is proposed by the Satokat sensei. So he was very exciting when he discovered the Higgs boson. Then, so I'm sorry. So our universe is a spontaneous symmetry breaking like this one, but this energy is very small. But this energy is a factor, is larger by factor 10 to 30 or 10 to 40. So energy becomes very high. So big energy is created by the Big Bang after the inflation. So our universe has enormous energy. This is our current view of the universe. So he discovered Higgs boson make inflation or another undiscovered like a Higgs boson particle is make inflation. Now we have a big discussion about these topics, not yet decided. So we cannot say that I discovered Higgs boson make inflation, but similar vacuum field make inflation. We can say this point. So the basic idea is proved. So this is the reason why. So if the quantum fluctuation makes a small universe, here, there are many universes is created every 4 years, every time. So why only our universe becomes larger? So maybe that this question is not only our universe, but also many universes becomes larger. Now we consider. So many universes existing. So unit means only one. So currently we consider not universe, maybe the multiverse considered. So there are many universes existing in our world. So in this universe, this is our universe. In this case, so not only the human, but also the alien exist. But different universe, maybe the different physics law. So we don't know what happened. So maybe the physics law is also quite different. In the Greek, we see the many Greeks in these cities. So for the scientists, Greek looks like the mathematical formulas. So there are many mathematical formulas in the cities. So very difficult to understand. We consider what means this formula. Quite different, but so we don't know what happened. So maybe the different university is existing. I don't know that this is a science fiction or the science non-fiction. We don't know the answers. Also, we don't know how to check these ideas. Since even in this our universe, only the 10% we can observe, but another 90% we cannot observe. So outside of our universe, we don't know that. How many such universes exist? Some theorists said 10 to 500 multi-universe is existing. It means that 500 zeros. And another physicist, another theorist said 10 to 128. It means that 10 to 128 zeros is existing. It's crazy world. Yeah. I don't know how to explain. So this is we understand of what happened in the beginning of the universe. But Ceron did great jobs. What does KK? KK is also doing this. Yeah. So the Big Bang produced energies. So I have already said energy is the same number of the particles and antiparticles are produced using E equals mc squared. So the energy produced by the Big Bangs, and this means the same number of the particle and antiparticle should be existing. But in the current our universe, only the particle exists, and also small energy exists. No antiparticle is existing in our world. Why did antiparticle disappear? This is the second question. There are many questions in the particle physics, and after the Big Bang theory. So the small difference between the particle and antiparticles can banish antiparticles. This difference, particle physicists call the CP violation. It's very difficult, but so we call the CP violation. If the CP violation if the CP symmetry is violated, then the matter is produced slightly larger than the antimatter. Very slightly. Difference is only the 10 to minus 10. Very small difference makes our universe. Which part the violate, CP violate? There are two possibilities. The quark violates CP or the lepton violates CP. Which bet is very important. So, but Japan is very cheap. So we bet on both. So the super KB and bet on the quark sector. So the super KB, this is a circumference about 3 kilometers. That's about size is about smaller than factor 10. Comparing the C, but we make a big colliders, and using these colliders, we check of the CP violation of the quark sector. And also in Japan, the JPAC and T2K program probe to the lepton CP violation in the lepton sectors. In the JPAC, this is used for the heritage science, but also this is used for the neutrino science. We produced many neutrinos, and this neutrino is emitted to the Kamioka regions. Currently working the super Kamiokande, but in future it becomes more larger, hyper Kamiokandes. So this hyper Kamiokande project is started now. The funding approved was about 4 years ago. Construction by the KK and the University of Tokyo. And size of the water channel is about diameter is 70 meters, and also depth is also 70 meters. Very big water tanks. And there are many photomarch tubes. If the neutrino comes here, then sometimes scatter of this water, and this light is observed by the photomultitude. This is Kamiokande. Kamiokande, super Kamiokande, next is the hyper Kamiokande. Very easy scenarios. Yeah. And so this is a picture of the dome is already prepared, and now digging in the depths. So you can see that this picture of the domes. So this is the next minister visited this autumn. This is also international collaboration, and this program will be started maybe 2027, sorry. So let's join. Cyprus is welcome to the joining the Kamiokande programs. So the last ones. So insanity of the beginning of the university is very important. So the vacuum plays an important role. And also the inflation is very important. So the Higgs field is hidden in your vacuum, and it means the vacuum is not empty. And now discussing discovered Higgs boson or origin of the inflation or another Higgs-like field of the origin of the inflation. Now we are discussing. After the Big Bang, origin of the mass is also very important topic. KK and Japan is the take of this second question. And what the important things is what is time and space? So gravitational wave are already discovered. Gravitational wave means space and time is also oscillation. It's very strange. So space and time is not just constant and just not parameters. It also the object itself. So it moves. So what is space and time is very important. So gravitational waves, so it means space and time is also moved as waves. So that now we are using particles probe to the vacuum, and also in futures we probe to the space and times. What is the space and what is the times? So this is the 21st century's vacuum and space crucial target for the particle physicists using particles. Previously, the particle physicists study of the particles, but now the particle became some more just tools. So now we probe to the vacuums and the space-times. So vacuum, we relatively well understanding of the vacuums. Next time is space and times. So the gravitational is very important for the next future of the particle physics. So thank you very much.
Thank you, Asai-san. So the session is open for questions. Any level of questions are welcome.
Very difficult.
Okay, and over there. Wait for the microphone, please.
Could the missing particle be sound? The missing particle be sound that creates shape.
Missing particle shape?
Yeah, the particle that creates shape to things could be a sound. Vibration.
So you can understand. Talking about the dark matter? Maybe. So currently, we say only about 5% of the energy is understood. Sorry, 5%, sorry. For example, about 20% is the dark matter. We don't know what is the dark matter. And also about 70% is the dark energy. Dark energy currently is the expand of our universe. Maybe the origin of the dark energy is a different type of the Higgs boson. Maybe this energy scale is a milli-electron volt. But dark matter is a very difficult question. So I believe supersymmetry. So if person the supersymmetry believes that supersymmetry is like a neutralino in the dark matter. Neutralino means the photon supersymmetric particles and also W of the supersymmetric particle became the neutralinos. Maybe this is dark matters. In this case, energy of the dark matter, mass of the neutralino dark matter is about 1 to 3 tera electron volt. Current limit is about maybe 500. So we need more the factor 6 or 8 is necessary. So this is the reason for why the serum prepared for the more large colliders. but very expensive there. Maybe 15 billion Swiss francs. LHC is about 4 billion Swiss francs, so factor 4 is expensive here. But dark matter is very important. So another approach is using for the direct detection of the dark matter. For example, some precision detector is installed in the underground. Underground is cosmic background is very low. So then we detect it for, we search for the, some detection. But in this case, if we even in the discovered some signals, but in this case, what is the dark matter? We understand dark matter exists, but what is the dark matter? In this case, the collider is necessary. So another approach is using for the cosmic ray. Since in our galaxy, center of in our galaxy, there are many dark matter exist. So the dark matter and dark matter collide. Then the ordinary particle emit. This becomes a more high energy cosmic ray. So the European laboratory makes for the big mirror to detect all the high energy cosmic rays. So in Paloma, the island of the Spanish, the Paloma, yeah, for the detection of this species. Yeah. But accelerator is necessary. What is the data?
Okay, over there. Wait for the microphone. Yes.
Yeah, thank you very much for this lecture. We have not discovered anything beyond the standard model.
Mm-hmm.
So now LHC with the high luminosity, do you think that we have a chance? And if not, how would we theorists proceed? Because a lot of these ideas, supersymmetry, technicolor, etc., are very old ideas actually.
Yes, so exactly speaking, we have already discovered beyond the standard model. Since neutrino oscillation is beyond the standard model discovery. Since standard model is neutrino is massless, but the neutrino oscillation means the neutrino has a mass. So the beyond the this is exactly speaking.
But no new particle.
So
no new particle.
important things is Higgs mass. Higgs mass is 100. Sorry, it is not so. It's a professional discussion. I'm sorry. Higgs mass is if the Higgs mass is 120 GeV. In this case, supersymmetry mass is about 1 TeV. In this case, it has already discovered, but not discovered. It means the supersymmetry dies. But the observed Higgs boson mass is 125 GeVs. It means the Suji scale is about 10 TeV or something. Current limit of the supersymmetry is about just 1 TeV. So I think maybe that there are some possibilities. Of course, in this case, we can ignore it for the naturalness. But naturalness is, as I have already said, there are many universities exist. In this case, naturalness is not so important. Well, this is just one idea. So technicolor is already excluded since learning coupling with the precisely excluded this one. So I think maybe the 10 TeV or 100 TeV supersymmetry is still existing.
Yeah, but I mean, supersymmetry has also been excluded in many domains, right? So
just collider. So for example, currently, if we ignore, if we discovered for the Venus up to the 1 TeV, then so even in high FCC HH discovered does not discover the supersymmetry. In this case, maybe the supersymmetry dies. Yeah. But supersymmetry idea is very beautiful. So breaking scale is I don't know. Yeah.
Actually,
Yeah.
Okay. Another question?
Supersymmetry is a very beautiful idea. Yeah. Supersymmetry is so you image our space is 3 dimension, x, y, z, plus times. The time is the same as the space, just imaginaries. So 4-dimensional, but if why the spin is existing, spin 1/2, spin half means our universe is not only the one turns. The spin 1/2 particles means that it becomes opposite and second times turns the same. So our world is not so simple. So x, y, z is not so the particle physics. So x, y, z plus opposite and different sides. This is our space structure for the particles. So I think maybe the understanding of this structure, the supersymmetry is very important idea. So you just believe for our universe is only the x, y, z plus t's, but for the particle view is quite different. X, y, z plus positive side and negative side. So why the existing of this structure? So this is supersymmetry plays the important roles of this understanding.
Okay. Another question?
Sorry, it's very difficult.
More easier question. Okay.
Yeah.
Thank you very much for a very interesting talk. So I'm not the professional of this field, so maybe it's a stupid question, but could you go back to the explanation about the Big Bang and also the Higgs field?
Here?
I could, there is a Big Bang picture left bottom, and maybe the beginning of the...
Maybe.
sorry. After the discovery, maybe next, yes, that one. Yes.
Here?
So you're talking about the Higgs field, energy of the Higgs field and its Big Bang. So my question is, I couldn't follow why the Higgs field has energy.
Yeah, very big. If something exists, then the energy should be exist. Exactly speaking, energy is just difference of the state. So nothing or something. So absolute energy scale is just determined by the curvature of the space. So Einstein equation means so curvature of our universe equal of the energy scale. So the flat means the energy equals 0. Curvature means something energy. So it's very difficult. So here is a very high energy is existing. Discover of the Higgs boson means here is a very high energy exists. But our universe is almost completely flat. It's a very difficult question. We have not still answer of this question. If the naturally considered, this is the big energy that exists here. In this case, our universe of time and space curvature is very quickly changed. So our flat universe does not exist, but our universe exists. So maybe the Einstein equation is wrong. So Einstein equation is correct for the large scale, but for the small scale, so we don't know the Einstein equation. This is the reason why the gravitational at the particle level becomes more important. Currently, we don't understand of the Einstein equation versus quantum theories. It's quite different theories. We cannot unify these ones. Unified is very important for the particle physicists. So this is the understanding. Yeah. So this is the energy that exists, but this energy does not change space and time. Yeah.
Thank you very much.
Other questions?
exactly speaking. Let's imagine of the cubic of the sugars, very small ones. In this space, 10 to 46 proton is existing. If the same energy, Higgs is existing here. So the Higgs has energies. Its energy is corresponding to the 10 to 56 proton per cc. Very high energies is existing here, but does not affect over the space and time.
Okay, over there. Yeah, we just wait for the microphone, please.
A follow-up, maybe. So if this energy does not affect our space and time, how did the experiments change that in order to be able to detect this change?
Yes, does not affect the solidity. Yeah. Since we don't know the answer of this question. Yeah. So the important thing is that we have to consider two things. For example, the small particle, how to field of the gravities. Currently, the Italian group has tried to understand this question. They make atoms, very cold atoms, and drop, and then they feel the same gravity. So it means that atomic levels, so for the same gravity is observed. But elementary particle physics levels, there are no experiments of this. Second question is what makes gravities? So graviton makes gravities, but our gravity is not. You are feeling gravities. I'm standing over here is feeling gravities, but our feeling gravity is a fake field. Just the curvature of our space is curved, but the person just feels not just I'm straight, not field, not covered, not covered. Yeah. So in this case, so the just field movement is just covered, but person considered I just for the moved forward. This difference field in the gravities. So this is the gravities. But what is the problem? What is the makes of the curvature of our space? Einstein equation shows that energy makes some curvature. But why the energy exists in the space and time change, curve? It's a very difficult question. There are no answers to this one. So in this case, I think maybe about 10 years ago, so the high energy laser laboratory in the University of Osaka, they make some megawatt laser. If the megawatt laser disappear, then the curvature should be changed. So I tried to detect this one, but the change is very small, 10 to minus 27 or something. So we don't have such a detector now. So yeah.
Thank you.
Yeah.
Any other question? More simpler question is welcome.
So I have already said only 5% of our universe is understanding. 95% is we don't know.
Okay, if there are no other questions, let's thank Asai-san again.
Thank you very much.
Your Excellencies, ladies and gentlemen, colleagues, dear friends, thank you once more again for joining us for this riveting public lecture on this wide-ranging look at our universe, multiverse. I will never look at the ancient Greek inscriptions in the same way. I hope you will also remember this evening we shared together in this space with Professor Asai when you next view some ancient inscriptions in Greek. Thank you so much, Professor Asai. And now it is my great pleasure to cordially invite you all to join us for a very special reception kindly offered to you by the Embassy of Japan in Cyprus. Thank you, Your Excellency. Authentic Japanese sake. And I think in this cold November Cyprus night, we have all deserved it. Please enjoy the rest of your evening, and thank you very much indeed for coming. Please.